In this section, we'll discuss the operating conditions or variables that affect cat cracker yields and look at how these factors are controlled. You already learned that the goal in cat cracking is to convert heavy hydrocarbons into lighter, more useful molecules. To determine how much cracking occurs in a unit, we use a measure called conversion. Conversion tells us what percent of the feed has been cracked into material that boils below 430 degrees Fahrenheit. The boiling temperature of the cat cracker feed ranges from around 600 degrees Fahrenheit to 1,000 degrees Fahrenheit. So cat cracker products that boil below 430 degrees Fahrenheit must be composed of hydrocarbons that have been broken down from larger molecules. Conversion is normally calculated by measuring the yield of products that boil above 430 degrees Fahrenheit and then subtracting this figure from 100. In this example, 40% of the cat cracking products boil above 430 degrees Fahrenheit. So the percent conversion is 100 minus 40, or 60%. There are a number of factors or variables that affect conversion in the catalytic cracking process. One important factor is the type of catalyst that's used. Different catalysts produce a different range of products. Some catalysts maximize the production of high-octane gasoline. Others increase the yield of jet fuel. The term catalyst selectivity is used to describe the product distribution that can be realized from a given catalyst. The ability of the catalyst to actually convert the feed into lighter products is called the catalyst activity. The more active the catalyst, the higher the rate of conversion. High regenerator temperatures or contaminants in the feed can gradually reduce the catalyst activity and selectivity. Fresh catalyst is added as needed to maintain the desired activity and selectivity, and also to make up for catalyst losses in the flue gas and fractionator bottoms. Another important operating variable is the catalyst circulation rate. Catalyst circulation can be measured by two different methods. The first is called weight per hourly space velocity. The space velocity is determined by dividing the pounds per hour of feed charged to the unit by the total pounds of catalyst holed up in the reactor. The space velocity is usually changed by adjusting the catalyst level or hold up in the reactor. When the catalyst inventory in the reactor is increased, there is a corresponding increase in conversion. This, however, may not be desirable because increasing the contact time between the oil and the catalyst often leads to overcracking. When the oil is overcracked, less gasoline is produced in return for higher gas and coke yields. The majority of cat cracking units in operation today are pure riser crackers. In these units, a bed of catalyst is not maintained in the reactor, so space velocity, or holdup, is not a relevant factor. Instead, the catalyst circulation is determined by measuring the catalyst-to-oil ratio. The catalyst-to-oil ratio is simply the catalyst rate divided by the feed rate. As more catalyst is circulated through the system, the catalyst-to-oil ratio increases. You can see from the graph that conversion increases as the catalyst-to-oil ratio rises. A third operating variable is the reactor temperature. The temperature in the reactor is controlled by adjusting the feed temperature, by changing the amount of bottom product recycled, or by changing the catalyst circulation rate. This chart shows the relationship between reactor temperature and conversion. Generally, high reactor temperatures are desirable because they increase the gasoline yield and octane number. A fourth operating variable is the regenerator temperature. The regenerator temperature is a function of several other variables, such as the amount of coke on the spent catalyst, the degree to which carbon monoxide is combusted to carbon dioxide, the catalyst circulation rate through the regenerator, and the amount of air supplied by the air blower. High regenerator temperatures are often maintained because they reduce the amount of coke on the regenerated catalyst. The high regenerator temperatures also increase the amount of heat that the catalyst absorbs, so less catalyst can be circulated to meet the process heat requirements. The amount of coke that remains on the regenerated catalyst is also considered an operating variable. This is because coke deactivates the catalyst. Conversion decreases as the amount of coke on the regenerated catalyst increases. Another variable that affects yields is the amount of bottom product that is returned to the reactor from the fractionator. This variable is called the recycle rate. Increasing the amount of recycle results in higher conversion and greater yields of gasoline and coke. In most operations, however, a low recycle rate is used because of the problems caused by the coke. The feed preheat temperature is also a factor that affects the unit operation. Raising the feed temperature means that less heat is needed from the catalyst, so the catalyst circulation rate can be reduced. This reduces the coke yield and increases the unit's capacity to process feed. The maximum feed preheat temperature is normally around 800 degrees Fahrenheit. Temperatures higher than this will cause thermal cracking inside the heater. The air to the regenerator is another operating variable. The burning air rate is set by the amount of coke produced. Enough air must be added to the regenerator to burn the coke off the catalyst. But if too much air is added, excessive burning will cause high regenerator temperatures. Pressure in the reactor and the regenerator must be controlled to maintain the proper catalyst circulation. These variables, however, have little effect on product yields, so they are normally not adjusted to influence conversion. The composition of the feed affects what types of products a particular unit will produce. This is because different types of hydrocarbons crack in different ways. By carefully analyzing the feed, we are able to predict the product yields.